Hello everybody, my name is Andrew Dunning and I'm going to be giving a short presentation here on the geology of Death Valley National Park in California in the United States. I'm going to sort of wait a few minutes here on and off just to let a few more people join since we have 44,000 members or so in our community and I see only 20 have joined so far, so hopefully more will come and we'll wait a little bit. I'll sort of give a short overview introduction before I dive into some of the bigger material. Death Valley National Park it's the largest national park in the continental United States, the contiguous 48 states, so really outside of Alaska. It's larger than 3 U.S. states, half a dozen territories in Puerto Rico, and 100 countries. It's a truly enormous place, and as part of that, it has incredibly varied geology. It really ended up in a fortuitous location to have almost every geological structure and feature that you learn about in your textbooks can be found in Death Valley and its surrounding area. I've got a number of samples here that exhibit some of the things I'll be talking about. I'll probably be showing a few pictures out of this book, A Trip Through Death Valley's Geologic Past by Kenneth E. Langer. It's a really great book with great pictures of a lot of the geologic formations found in the park. I've been there 25 times now, and I've gone through quite a lot of it, but still, there's enough for me to see to last me the rest of my life and several more. I've got a few more people now. I'll dive into this. So Death Valley National Park, welcome. It's my favorite place to go visit, although I live in Oregon now, so we can only get down there a couple of times a year. It's the hottest, driest, and lowest location in North America. Lowest altitude, minus 86 meters, so it's 86 meters below sea level, down in the bottom of the salt pan. It's the hottest, 134 degrees Fahrenheit, 56.7 Celsius. And that was found in 1913 in the height of summer. And it's the driest desert in North America. They see fewer than 5 centimeters. That's 8 centimeters of precipitation a year. So very dry, very hot, often very windy. I've been there in windstorms of 80, 90 kilometers an hour. It can be very windy there. Humans in Death Valley go back about 9,000 years. There's ancient indigenous and Native American peoples that go back for many thousands of years, tons of artifacts littered through the mountains. First Europeans came 1849, and it was given the name Death Valley after a member of their wagon party perished in the summer heat. It's been a hot spot for mining for gold, silver, lead, antimony, borax, fluorite. Hundreds of different minerals and metals have been mined in Death Valley. And it was protected as a national monument first in 1933, before becoming a national park in 1991, where it was greatly expanded. And it was expanded again this last year. It is now, that's 44,000 square kilometers. 13,000 square kilometers. It's huge. It's about the same size of Puerto Rico. And the rocks in Death Valley go back 1.7 billion years. The oldest rocks in the Death Valley go back to 1.7 billion years. So let's start there at the deep time, 1.7 billion years ago. These are schists and gneisses, so these are really high-grade metamorphic rocks. So they've been deep and buried underground under the surface for a very long time before they got shoved back up to the surface relatively recently and quickly. They call it the crystalline basement because it is really the roots of our continent. This is deep from the interior of the North American continent, so they've been there a really long time. Some estimates have placed, so these were created from sedimentary rocks, old limestones and ocean bottoms, and some people have put those at 2.5 billion years old. This is part of a supercontinent, an ancient form of, continents all shoved together called Columbia, where it formed a passive margin, it's called, sort of like the east coast of the United States today, where it's not near there's no deformation going on, just sedimentation, so rock is just continuously being created for millions and millions and millions of years. So these very oldest rocks, these 1.7 billion year old gneisses, have been shoved up into what are called turtlebacks, these huge sort of rounded ridges, and I'll talk more about those a little bit later. But getting into the sort of the visible geologic history that we can understand and interpret, we get to 1.3 billion years ago, the oldest sedimentary rocks. These are limestones, dolomites, and mudstones from the Johnny Formation, the Dolomite, Noonday Dolomite. These are very, very old rocks, hundreds of millions of years, sort of 1.3 billion to about 500 million. It's the oldest Proterozoic rocks. And they include fossils of stromatolites, the oldest sort of big visible living things that we have in our rock record. The Noonday Dolomite and the Kingston Peak Formation I'm pointing out specifically because they have evidence of snowball Earth events where all of or most of the Earth probably froze over and glaciated, with sea ice going down into the tropical latitudes. So these rocks, the Dolomites and the Kingston Peak Formation, before the evidence of this snowball Earth is we can see with fossils and some other techniques that it was tropical in latitude. So this is sort of between 20 and 30 degrees latitude above the equator. And these the snowball Earth evidence is we find what are called drop stones. So an iceberg floating in the ocean sometimes will have rocks stuck to the bottom of it, and as it melts and it thaws, these rocks will fall out and crash to the ocean floor. And I don't have a picture of it handy, but you can see it really clearly in outcrop. I'll post some in the comments after I'm done talking here, where these rocks clearly landed into mud and deformed it, and they're really cool. There's tons of these through the park, and have created some great evidence for snowball Earths that has been used to correlate around the world. Let's see. We've recorded sequences with these rocks of rising and falling shallow seas. So if you picture the east coast of the United States, where there's this broad coastal plain and this sort of shallow continental shelf, that's really the kind of environment we're looking at here. And so really after the Cambrian explosion, where we start to see more and more animals and animals that exist today, and fossils of those begin to show up in the limestones and dolomites that make up really the bulk of what we see in Death Valley. So these limestone shales and sandstones after the Cambrian period, the Cambrian explosion, sea level changes visible in the Bird Spring Formation has been used, which is a interesting limestone and dolomite formation in the Panamint Mountains. And through that, we've been able to establish sea level changes. There's a really interesting paper published in 1999, specifically in Marble Canyon, which is a great tourist location in the park, that deals with sea level change in limestone from, let's see, what is that, 400 million years ago. It's really cool. Seas were pretty warm. There's very early corals that start to show up around that time. The Tin Mountain Limestone is my personal favorite formation in the park for no reason other than it's really pretty. It's this blue limestone, and the fossils in it turn out this kind of bright orange color. I have a sample of it here that was collected outside the park. You can see this sort of bluish limestone, and all of these sort of round features are all rugose coral fossils. It's also called a horn coral. These are very early types of coral that sort of made these ice cream cone shapes coming up from the ocean floor. They didn't form reefs like we see coral doing nowadays. Also in these limestones, we have what are called algae nodules. I have another one here, also collected outside the park. This is from the Bird Spring Formation, and these, you see them in outcrop. They're these beautiful orange, sort of cherty, almost glassy-looking nodules, perfectly round sometimes, sort of globs. And they're remnants of algae that were living hundreds of millions of years ago that are now tilted at these crazy angles and make these great, excellent photos. I'll post some of those in the comments afterwards as well. So Death Valley's sort of sedimentation period, where all of these limestones and dolomites are being deposited, ends at the earliest days of the Pennsylvanian period, 350 million years ago. And after that, rocks were probably still being deposited, but they are not recorded. They got eroded away. So we have a big unconformity of these depositional environments that lasts from 350 million years ago up to the Miocene, so about 30 million years ago. That's the Oligocene. But most of the depositional rocks we have don't start to show up until the Miocene and 20 million years ago. There's a few things in there, but Mostly it's empty, apart from these big granite plutons, a big intrusion of magma that came up under the ground. And that's related to the Sierra Nevada mountains, which are just a few tens of kilometers away. This is Yosemite, Sequoia, Kings Canyon. These huge granitic spires and mountains, these really dramatic mountains, are all granites that date to about 200 million years ago, when the tectonics changed and the continents started to rearrange themselves. And Death Valley went from a passive margin to an active margin, which means the oceanic plate started colliding with that ancient Paleo North America and started to go underneath. Rocks became folded and uplifted and run over each other, and this subducting oceanic plate began to melt and melt rocks around it, which then rose up and created these plutons, this huge batholith that stretches from effectively Los Angeles almost to Oregon of solid granitic rocks. And this started about 200 million years ago in the Jurassic period. So we don't have any surface rocks and therefore no dinosaurs from this period. But we do have these granitic rocks, which helped form mineralizations in the nearby host rocks that allowed for some of the mining booms of the 19th and 20th centuries to take off in Death Valley and put it on the map as a hotspot for human activity. So it's also in this time where we start to get these granites forming. There's a number of them in the Panamint Mountains, a big one called Hunter Mountain, and I have a piece of that from just slightly outside the park boundary, a piece of that here. This is classified as a quartz monzonite. So I can get it to focus on that. Nope. But it's mostly quartz, a little bit of feldspar, and biotite in it. It's a really beautiful... Ooh, there's a garnet right here. You can't see that. That's really annoying. But it's a beautiful rock, beautiful white quartz monzonite. Looks a lot like a diorite. And, ooh, I have another piece of this limestone here. The cool thing about this piece of limestone, I don't know which formation this is from. However, it does include a chunk of galena. So I know it's from nearby one of the many plutons in the area. So as hot fluids surrounding these intrusions of magma sort of infiltrate the rocks around them, they deposit quartz and, in this case, lead sulfides. This would have been something that miners were looking for back in the mining days. Similarly is this piece, which, nothing dramatic to see, but it's got some quartz in it, so we know it is from near one of those plutons where mineralization was happening. See, that takes us to the Cretaceous, or the end of the Cretaceous, rather, the Paleogene. And this large regional deformation that was happening from the collision of the two continents was starting to deform the rocks in Death Valley. These huge flat limestone beds were being pushed and bowed up, so there's huge folds and faults and dramatic shapes, and everything's at crazy angles now in the mountains around Death Valley. And some of these big thrust faults where a young rock gets pushed on top of older rock, or sometimes older rock gets pushed on top of younger rock, so you have these repeated stratigraphy sections and places where rock is upside down. All these crazy folds and different amazing deformation happens because of the collision of these two continents, of the oceanic plate, the Farallon plate, and the North American plate. So about 20 million years ago, this subduction stopped occurring, and about 30 million... I have that backwards. About 30 million years ago, subduction stops for the most part, and we start to get a sliding of plates rather than a crashing of plates, and that's the genesis of the San Andreas Fault, which is now world famous for being both the source of earthquakes and for being a beautiful transformed continental plate boundary, where the two continental plates are sliding together. We'll get back to that a little bit later when we get to the formation of the valley itself. We're still just in the rocks. All of this is just rocks. So these mountains began eroding when that happened, and the Death Valley began to be sort of flattened out. So we have these broad savanna plains with streams and maybe small hills and volcanoes. The earliest volcanics start to show up in the early 30 million years, late 20 million years time period. Hi, Charlie. This is my quarantine. Yes, hello, everybody. If you're from the West Coast, say hi. If you're from international, say hi. Please interact with me. I'm here to answer your questions. So back to Death Valley now. Where was I? Volcanics. All these volcanics start to show up in the late 20 million years to the early 20 million years, all through Nevada and all through California. If you look at this on Google Earth, you might be able to see some of it. I've been looking at it a long time, so I see it all. But for some reason, all these big caldera eruptions start showing up. And that may be related to the formation of the Basin and Range Province as a whole, which is that whole region stretching from Death Valley really up to Salt Lake City in Utah and north into Oregon, where you have all these basins and really high topography and mountains and valleys, and it's very interesting. It's really unusual in the world. There's a number of different ways it could have formed, and it could be related to, hello, Susanna from Africa. And it's probably related to deep mantle activity rising up and bringing magma closer to the surface, which would result in volcanism. And some of these huge caldera eruptions, super eruptions, think Yellowstone, blanketed the Death Valley area many, many times over millions of years. So we have a thick sequence of volcanics. Most of that is found in what are called the Black Mountains. If you pull up Google Earth right now and start to look at Death Valley, you'll see the Panamint Mountains on the west, which are huge. They're close to 3,000 meters high. And then there's the Black Mountains on the east, which are a little bit smaller and are mostly made of these... I was talking about those 1.7 billion year old gneisses earlier, and they're found in the Black Mountains. And on top of that is a gap of 1.7 billion years. And on top of that, you have young volcanics, really from 20 million years to the present. Or more recent than that, rather. And so all these volcanics, you start to get these are called tuffs. You get a lot of these big ash flow tuffs. And you start to get... And the magmatic sources of these are debated today. They've been being studied for 60, 70 years, and there's still a lot of debate going on about them. They're very, very interesting. I've done a little bit of research this on myself, but certainly nothing I can publish, since I don't have any geochemistry data, but that's not important right now. We get back to the volcanics. We start to get lava flows and more of these ash tuffs that slowly build up the topography to be a bit more rugged. The climate and the topography is really like a lot of parts of Africa, where you have these flat savannas punctuated by these huge volcanoes. It's really... hello, Erica. Hello, Jana Belshanikan from Utah. We got Hungary. We got Peru, Pakistan, Switzerland, Spain, Brazil. Wow. Indonesia. Wow. People from all over the place. Thank you all for joining. I appreciate it. Volcanics. The volcanics are fantastic. They also allowed for a lot more mineralization to occur, which facilitated metal deposits and mining interests, which furthered the human story, which we'll probably get to a little bit later if there's time. So right as all this volcanism is happening, the tectonic regime sort of changes again. The San Andreas Fault is starting to form hundreds of kilometers to the west, closer to the ocean, but its effect is stretching across the continent. Many sort of mostly parallel fault zones begin to appear, including the Death Valley Fault Zone, south and north. There's sort of two sections of it. And they're accommodating this north-south movement. That's called a diffuse margin, where the strain from these two continents sliding past each other is sort of being propagated across, because the continental crust is pretty ductile. It can sort of bend and break more easily than the oceanic crust does. And that means that all these parallel fault zones begin to appear. And related to all of the uplift that was happening and forming the basin and range, which is really complicated, really high-level stuff that is difficult to understand for a lot of people. Many researchers sort of argue about this all the time. And when all these parallel fault zones start forming, pull-apart basins start to occur between them. So you have the southern Death Valley Fault Zone and the northern Death Valley Fault Zone. The southern Death Valley Fault Zone is moving this way. The northern Death Valley Fault Zone is also moving this way. But it creates an area of tension where it's getting stretched between the Panamint Mountains and the Black Mountains. And so that formed some pre-existing structure way deep down into the billion-year-old metamorphic rock. And that caused them to shoot up. They rose really quickly. And the Panamint Mountains tilted down, and the Black Mountains tilted up, so you get this huge detachment fault, where these two huge chunks of the continent start sliding past each other. And that allows for Death Valley to drop down much deeper than all of the other valleys around it. Because that pre-existing, that detachment fault where the two mountain blocks start to come apart and move past each other really dramatically is not seen in any of the other parallel valleys north to the south, really anywhere else in the Basin and Range system. And Marlee Miller from the University of Oregon has done a lot of research on this, and her website, if you Google Marlee Miller, you'll come across her research. She's done a lot of really interesting work studying the metamorphic structures and the fault planes and all sorts of crazy stuff, trying to figure out, put together this puzzle of why is Death Valley so much deeper than everything else? And what is the history behind it? Why did it come apart to be so much deeper than everything else? So that all happened before you probably would have been able to see much on the surface. So about 15 million years ago, most of these valleys started to drop down. You would have had mountains and hills starting to uplift with erosion, and some of these valleys started to drop down and get filled with lakes. So we have a lot of this sort of lake mud sediments around Death Valley, and a lot of these have fossil footprints and fossil animal bones in them. There's a place in Death Valley that you can only get to with rangers, where the walls of the canyon are covered in footprints and trails and fossils, and it's really cool, and I haven't been there, but I would really like to be. So these spring-fed lakes that started to appear during this time, about 15 million years ago, were then covered with more volcanics, and then the valley started rifting apart more dramatically, and the bottom dropped down, and the mountains shot up, and so you have chunks of these. This lake sediment is now diagonal, placed thousands of feet, hundreds of meters higher up on the mountains than the valley floor, which is really cool. It's really neat to see lake sediments at a 45-degree angle, sticking out with footprints going up all the way to the side of it. Yeah, wow, indeed. Animal fossils. So we get to the Ice Age. We're now pretty present. We've gone from 1.7 billion years ago to the present, more or less, much more recent. We're in the Holocene, in the Quaternary period. So the Ice Age is going on. The most recent Ice Age is going on. And there's increased precipitation in the area. The temperatures are cooler. There's less evaporation. So the lakes, the valleys all fill up with lakes from melting glacier water and increased precipitation. I have lots of dolomite from Death Valley, jazzy. And so as these lakes are filling up, they start to leave shorelines in the valley walls and on the mountains next to them. There's a place called Shoreline Butte in the very southernmost end of the valley that has several dozen of these shorelines are carved into the cliff, and there's a number of beaches preserved on some of the big alluvial fans. And so this lake was called Lake Manly, after one of the first Europeans to enter Death Valley, William Manly, which is a pretty cool name, I think. And this lake is 600 feet deep, 200 meters or so. Could have been deeper than that even, since some of the shorelines have been eroded away. But this chain of lakes would have stretched from the Sierra Nevadas and may have even reached the Colorado River, which is hundreds of kilometers away, down closer to Las Vegas or Needles, California. If you look at this on Google Earth, it can all make sense, and how vast the distance is and how enormous the system of lakes, how much water would have been present. But the Ice Age ends 12,000 years ago or so. And so this huge 600-foot deep lake dries up. The temperatures start to heat up, the climate changes, and there's no more water being fed into it. So it dries up and leaves behind this enormous salt flat, this beautiful white surface across the bottom of the lake, across the bottom of the valley where the lake used to be, this big lake bed. And it deposits salt, it deposits chlorites, carbonates, and borax, which is a industrial mineral used in metal smelting. It's used in soaps. It's used in tons and tons of processes. It's a very valuable mineral. And so in the 1870s and the 1880s, people started collecting it and finding it and processing it in Death Valley. And they really started the first long-term European presence in the valley was borax mines. Gold mining and silver mining and other metals had started to occur as early as the 1850s, but really in the 1870s and the 1880s, people start pouring into Death Valley. I'm going to talk about the alluvial fans for a little bit now. So Death Valley is a very arid environment. It's very hot, it's very dry, there's very little precipitation. So the mountains do erode. They are being uplifted pretty quickly, so their stream gradients are really steep, and that means they want to flatten out. So they carve these deep, narrow gorges in the mountains and dump tons of sediment into the valley where it starts to get kind of flatter. And so there's numerous events of sedimentation and alluvial fans existing in Death Valley, in the greater Death Valley area. I have a chunk of a similar one from a nearby valley here. Yes, the lake was absolutely saline enough to make a salt layer, and there's numerous of them. There have been drill tests done through the sediment, which is, I think the sediment package at the bottom of Death Valley, I'm trying to remember here. It's in one of these books I have in front of me, but I'm not going to look at that yet. The salt layer, there's numerous salt layers going down for, see, it's about 12,000 feet, so 3,000 to 4,000 meters of sediment, gravel, and salt exists below the visible valley floor of Death Valley before we get into the very old limestones and other stuff that we were talking about earlier. But this is called alluvium. You can see this sort of red clay sedimentation in these angular clasts. This is very typical of many alluvial fans around the world. So all these stream channels are dumping out flash flood deposits and sediment and gravel and big rocks onto the valley floor, and they start to pile up into these big slopes. Because of the sort of uneven subsidence in Death Valley, the alluvial fans on one side, on the Panamint Mountain side, are 5-6 miles long. They're very long, very steep. They go up 500 meters in height. They're very tall, very long. Whereas on the east side, where the Black Mountains are, the salt is being pushed up over them, so the alluvial fans will get buried. And so they make much nicer, rounder shapes. And if you look at it in Google Earth, Google Maps, you'll see sort of classic alluvial fan shapes and morphology on the Black Mountain side. On the surface of these alluvial fans, they're very long-lived surfaces. Some of them have been estimated that, some of these high surfaces may have been undisturbed for 20,000 years. And sort of an interesting side effect of that, some of these limestones, I don't know if you can see it, but this is really rough. It feels like really coarse sandpaper. This is, I believe, a Tin Mountain limestone. I collected this in Panamint Valley, which is the next valley to the west. And so it does have these harder calcite chunks in it. Those could be fossil remains. They could be what we call wacky, which is just a lithic sediments, just a chunk of rock stuck in the limestone. I haven't looked at it too closely, although there is a small crinoid fossil right there, which I hadn't noticed before. But anyway, the surface of these alluvial fans are very stable and may not move for thousands and thousands and thousands of years without being disturbed. And just even though the little precipitation that they get in Death Valley is enough to chemically etch the surface of these limestones, because rainwater is naturally acidic and acid eats away limestone, so you can get the carbonate will dissolve away and leave some of these harder lithic chunks in these limestones, leaving these really coarse surfaces on many of these surface rocks. When I learned that was very interesting. Charles B. Hunt did that in his excellent book, Death Valley, Geology, Ecology, and Archaeology, is one of the gold standard books, really, from that, of the Death Valley geologic story. There's enough geoscience in Death Valley and enough variety to amuse the intrepid researcher for their entire lives. The first geologists entered Death Valley in the 1870s, and research is still being done today, and it will never be done because it is such a vast area with so many different stories to tell. See, have I missed anything? I can talk about the turtlebacks now a little bit. Those are really interesting. So these 1.7 billion year old metamorphic rocks got uplifted and bent into these huge rounded ridges. And there may have been a pre-existing structural weakness in them, which is what Marley Miller, who I mentioned earlier, has been studying. And she was looking at various deformation features inside the metamorphic rocks and some of the streaks along the fault plains called slickensides. She's been looking at those and the directions they go and how they change over time to establish why they're at the surface. Because these sort of continental basement rocks generally don't come to the surface unless something really weird happens. This is one of the only places they're found in the West, in the west of the United States, in the Southwest, especially California, Nevada, Arizona. So and it is really hard to understand, even for me, why exactly it happened. But the leading idea that most people have agreed on is that there was some kind of structural weakness that happened during the change between subduction and transform plate movement that allowed that once basin and range extension happened, this structural weakness allowed the basement rock, this gneiss, to move up more than the surrounding topography and mountains. Which is really interesting because the Black Mountains are not very high. 2,000 meters, I think, is their highest point, roundabout. Whereas the Panamint Mountains just across the valley are nearly twice as high, 2,500, nearly 3,000 meters in places. There's a lot of really interesting stuff going on, and it all could have some relation to the uplift of the Sierra Nevadas, and mantle plume dynamics. There's a whole lot of theories that are going on, and it's a very interesting, however, unfortunately not very active field of research. All right, are there any questions? There's a lot of material. I've been going at this quite a while, and it can be really difficult to condense 1.7 billion years into a clear, concise kind of storyline. So sort of to summarize, in case you missed the beginning, we went from a continental shelf environment, a shallow sea, that lasted from 1.3 billion years or so up to about 350 million years, depositing tens of thousands of meters of limestones. From there, we get mountain building and erosion and granitic plutons and stuff, magma intrusions that have formed some of the other higher mountains, and mineralization that led to mining and silver and gold and all that sort of stuff. And then we have volcanics combined with a transition to extension, to where mountains are being pulled apart from each other and valleys are dropping down between them, in part accommodating north-south stress movement from the San Andreas system. How big are the turtlebacks? Hi, Brian. The turtlebacks are... I've got my Google Earth handy here. Let me take a look. Much of their structure is most likely below the surface. I can tell you right now, one of the major ones is called the Badwater turtleback. And there's a viewpoint you can drive to which sits at the very top of that, called Dante's View. And this is probably the most easily visible, easy identified one. This huge, big, sort of smoothish, roundish ridge of dark rock. And on top of that, there's a viewpoint called Dante's View. So that's visible from Badwater, which is the lowest part, 86 meters below sea level. And the top of Dante's View is 1.65 kilometers. I know it's about 5,500 feet. So that's 1,650 meters-ish. And that's what's visible. You know, this rock of this age and type probably goes down for many kilometers below the surface. Hi, Erica. Are all 400 meters of lake settlements from Lake Manly? So we got 4,000 meters of sort of deposited gravels and sediments and such below the visible valley floor. Most of those are probably alluvial, which meant the mountains were eroding into the valley while lakes were there, or maybe before the lakes were there. Mountains have been continuously eroding into this basin for the last 15 million years or so. So we've got 15 million years of sediments to sort of fill this big hole. But it really didn't start to subside quickly until about 1.5 million years ago. And I'm not exactly sure how they've determined those dates. I don't have that information handy. I know there's a number of different methods have been used to age sediments and estimate. There's a lot of estimating going on just based on what we can observe. We've measured fault scarps. The most recent fault scarp in Death Valley goes to, I believe it's been estimated about 2,000 years ago, would have been a magnitude 7.5 on the magnitude scale earthquake. quite a large earthquake. It goes for 75 kilometers, I believe, continuously. In places as much as 4 meters of offset. So if we do 4 meters over 2,000 years, give or take, the subsidence rate and earthquake fault slip rate on the Black Mountains fault turned out to be 3 millimeters, 5 millimeters a year. So pretty slow compared to the San Andreas fault, which is 35, 45 millimeters of slip a year. Hello, Keaton? Sorry, I don't know how to pronounce your name. Any other questions from anybody? I'm more than happy to sit here as long as you have questions and want to talk about this amazing, fascinating place. Unfortunately, there's quite a significant delay between when you type the question and when it appears in my feed here. So I may not see it for a minute or two. I can talk about... I'll show you some pictures from this book, The Trip Through Death Valley's Geologic Past. Oh, here we go. First page. This is a glacial drop stone. So this right here, you can see sort of that the rock layers are bent underneath it. Sort of like what you'd see if you dropped a bowling ball onto layers of foam. It would sort of sit there, it would deform the rock layers around it, and then you have sediment draped over the top of it. Other than coral, are there any other paleontological evidences in the limestones? Are the limestones ooidal in nature? So an ooid, for those of you who don't know, is a sort of calcite concretion that forms from both animal excretion and from natural processes. They're pretty bizarre, really weird, really cool. Oolitic limestone is a limestone that is made of lots of these little balls, 1 to 3 millimeters across, kind of look like BBs. There's no ooidal limestone in Death Valley. There aren't any really reefs either. A lot of the fossils are, you got brachiopods, brachiopods, there's mollusks, tons of mollusks. There's snails, clams, all sorts of stuff. Lots and lots of marine fossils. There is Precambrian fossils as well. There's some sort of jellyfish and what was that called? Lots of invertebrates. Ediacra, that's what it's called. Lots of Ediacaran sort of order fossils. Invertebrates, cnidarians. I don't know if there's fish. It wouldn't surprise me if there were fish fossils that old. I know it's mostly mollusks and sort of hard-bodied creatures. Although they're like this algae nodule, which I showed off a little earlier. This is this rugose coral. Vertebrate fossils are not found in the limestones, to my knowledge. There could be a fish or something older than that. But we do see vertebrate fossils post-Cretaceous. In the Titus Canyon Formation is a sort of alluvial surface environment like sandstone, conglomerate, mudstone, and it contains vertebrate bones of sort of ancient mammals. There's one called a titanothere, is the biggest one that I can think of offhand. There's considerable paleontological resources from sort of more modern mammals. There's mammal vertebrates present in Death Valley and in some of the lake sediments too. There's a mastodon in some sediments that was about 12,000 years old, so pretty recent. Hello from Colombia. Nice way to go through the quarantine. You showed us a rock with galena. Could you tell us more about the mineral development there? So I don't know a ton about mineralization and the genesis of galena and other sulfides. I know there are a lot of silver, lead, zinc, tin mines in the area. So this galena chunk formed in a limestone that was adjacent to this monzonite, magmatic pluton. So in terms of how the minerals developed there, I don't know. I know there's nearby where this was found, there's a lot of copper mines as well. I don't know if that tells you anything. Most of the stuff that's found in here, in this area, is lead, zinc, silver, and copper. What age are the glacial drop stones? I'm actually not certain what the age of some of these drop stones are. But I do know the rocks that contain them are about 750 million years old. Let's see if it's in this fancy book here. I'm more than happy to refer to the literature on this. There's a lot of good research on them. If you look up the Crystal Spring, the Noonday Dolomite, and the Bonanza, the Kingston Peak Formation and the Noonday Dolomite contain most of these glacial drop stones. I have seen one that was in a metamorphic marble in it's called Mosaic Canyon, which is one of the more popular tourist areas in Death Valley. You can see some of these drop stones in the marble there, which is pretty neat. Are there any human footprints present? Thank you, Brian. No, I do not believe there are any human footprint fossils that have been found. As far as I know, and as far as the understanding goes, humans as a species probably didn't even exist yet when those sediments were laid down. Most of the lake bed sediments are in the Miocene, so that's the Miocene stretches from 23 million to 5 million years, so there's several different lake period events in there that contain footprints and fossils. Obviously, that's way before humans or any sort of hominid ever existed. Paleozoic, yeah, they would have been Paleozoic, Proterozoic age glacial drop stones. Yes, this presentation will be recorded and will be saved on this group page. If you are interested in the rocks of Death Valley and for some great pictures of the rocks, I do highly recommend this book, A Trip Through Death Valley's Geologic Past. There's other books. There's so many books about Death Valley geology. I've got, half of my collection is in front of me. So for more recent, this USGS publication, it's just called Death Valley Geology by Wes Hildreth, gives a lot of aerial photos about sort of the fault movements and the evaporite minerals and sort of the mining history and the surface processes that have gone on and do continue to go on. Oh, I happened to turn to the page about the depth and the size of the salt flats. It's pretty dense reading, though, so I'm not going to read it. So the very top layer, someone was asking about how thick the salt layers are. The very top of it is a 1 to 1.5 meters thick bed of solid rock salt, 95% sodium chloride. That's pretty neat. Here's something cool. The racetrack Playa is one of the most notorious locations in Death Valley in that it has a really high visitation and people read about it on the internet a lot. It's a lake bed where the rocks move mysteriously across the surface and leave trails in the mud. So a lot of research has, the most significant research to really sort of nail it down was published a number of years ago, 2015 or 16, I believe. Other people have theorized that it could be aliens or wind pushes the rocks agically across the lake surface or magnetic vortices or other baloney made-up terms. But what does happen, so this lake is at about 2,000 meters in altitude. No. It's about 1,100 meters in altitude. 2014, thank you. 1,100 meters in altitude, it's about 3,500 feet. Most recent tectonic regime there. I'll finish talking about the racetrack Playa first. The lake's at pretty high altitude, and in the winter it gets snow, it gets rain. So a temporary shallow lake bed will form on this mud playa surface. And it freezes at night because it's at high altitude and it gets cold. And I mentioned the wind when I first started this. Wind speeds in Death Valley are vast. I've been there in windstorms that have knocked out power for the whole valley. The highest gust I remember being there that was recorded was 86 miles an hour. I don't know what that is in kilometers. It's a lot. Very, very high winds. It's sort of a natural wind tunnel, a lot of these parallel valleys are. And the racetrack Playa gets these winds as well. And so when this lake freezes at night, the wind pushes the ice sheet, and the ice sheet has enough kinetic energy to move rocks and drag trails in the mud. So that's really interesting. There's a number of other high-altitude playas in the area, including Bonnie Claire Lake, which is sort of to the northeast of Death Valley, a little bit farther to the north, that also exhibits these rock trails. What is the most recent tectonic regime there? Extensional. It's the Western North America is sort of very interesting in that it's part of it, half of it is an active margin. North of Cape Mendocino in California and up to Alaska, it's an active convergent margin. South of Cape Mendocino, it's a transform plate boundary. So there's compression up north and extension in the south. And so a lot of these parallel normal faults, so they're called normal faults, where the valley drops down, the mountain goes up. They also have a pretty strong north-south strike-slip motion. So it's an oblique. A lot of them are oblique faults where they move down and to the north when they rupture. And that north-south plate motion is really accommodated all the way from the Sierra Nevada mountains to the Rocky Mountains. There's faults in Colorado even that that are influenced by that north-south San Andreas type motion. Wow, indeed. It's really complicated, and when these faults do rupture, there's the most recent big oblique fault rupture was the Dixie Valley earthquake in 1954. That was sort of in north central Nevada. Was that state? You can look this up. It was pretty big. It was 7 point something, big earthquake, and it ruptured a number of other little faults along it as well. And that was sort of a type. It was a very good case, a very good instance of one of these oblique faults rupturing. It's pretty far removed from Death Valley, so we don't really know how the Death Valley system specifically behaves, and we won't until one of the faults in the area ruptures, and they may never rupture in human occupation there. Humans were obviously living there when it last ruptured 2,000 years ago. There was even still a small shallow lake there when the earthquake last happened in Death Valley. You may have heard on the news there was an earthquake sort of near Death Valley. Someone just mentioned that in the comments. Thanks, Jazzy. The Ridgecrest earthquake, it's really difficult to sort of put that in the context of Death Valley. Faults in Death Valley and the neighboring Panamint Valley more often they do have active microseismicity going on. They're all small earthquakes that'll happen there a few times a year, maybe smaller swarms. After the Ridgecrest earthquake, which is only about an hour and a half drive from Death Valley, some of the faults in and near Death Valley have been more active because that released a lot of strain. There was two good-sized earthquakes that happened there, a 6.4 and a 7.0. Maybe it was a 6.9. That sort of changed the stress regime a lot in the region. Both of those are really close to the Garlock Fault, which is the second largest fault in California. So the San Andreas is a right lateral. The Garlock Fault, which sort of goes perpendicular to the San Andreas, is a left lateral fault, which helps accommodate block rotation of the Sierras and the Mojave Desert and the Great Basin. All gets sort of concentrated in this area along the Garlock Fault and in the parallel north-south fault zones there. And exactly how the Ridgecrest earthquake is related to the Death Valley movement, I'm going to say not terribly, though the changing in the stress environments there and the strange shadows and all that other stuff that Jazzy and I were in the same earthquake geology class last year. And so, I don't know, it's weird. There's a lot of complicated stuff going on down there. That's why so many scientists were out there over the summer. It's complicated. Everything is complicated in seismology. You never took earthquake geology? That's nuts. It was great. Ashley was very excited by the Ridgecrest quake. Ashley Strige is our professor. She's a very good seismologist. She does a lot of research on the San Andreas and on some of the fracking-related earthquakes out in Oklahoma and the American Midwest. Any other questions? Happy to talk. Ubehebe crater. Ah, yes. Yeah, Jazzy, I did study your thesis stuff. That's right. Jazzy, one of the commenters here, did a thesis last year, an undergraduate thesis about sort of the timing and uplift of Cascadia subduction zone earthquakes. So off the coast of Oregon and Washington and California and parts of Canada is a big subduction zone, and periodically it ruptures in a mega thrust earthquake that, if it happened right now, would kill many thousands of people. 8.0, 9.0 size earthquakes, massive events. And Jazzy did research on the recurrence intervals of these. They had a slice of a tree that was buried in ocean mud at Netarts Bay in Oregon. And this is off topic from Death Valley completely, but I just think it's cool. Took a slice of that tree, carbon dated it, and found out exactly when it was inundated by a tsunami, a near field tsunami, which would have been caused by one of these Cascadia earthquakes. They're very off topic, very cool. Ubehebe crater. That's the most recent volcanism in Death Valley. It's estimated between 1,000 and 600 years ago. So very recent on any volcanological scale. Some magma rose along one of the fault zones and reached groundwater, maybe even shallow lake water, and exploded. It left a huge crater. It's called a maar, which is a steam-driven explosion. When magma reaches water or approaches water, that water turns to steam. And so you have this colossal, constant steam explosion that goes on for days, weeks, months, years. And there's about a half a dozen craters there that sort of overlap each other. The most recent one is called Ubehebe crater. It's big. It's very big. About 1 kilometer across, half a kilometer deep. Big. It's a big hole. And sort of these black cinders cover everywhere in that whole area. It kind of looks like the moon. Those kinds of things, we call those monogenetic, meaning they happen once in that location and don't really start up again. The California Volcanological Observatory does monitor Ubehebe crater, though we don't really expect it activating again. There are other volcanic events that have happened in the area. There's a number of hot springs nearby, so there is still heat down there close to the surface. It's really interesting. But it is probably not a threat to humanity as a whole in the area. I wonder if there's a chapter in. I'll have to look back up on that. Again, it's been a while since I've studied it. So we got active faulting, got recent volcanics, we got evaporite minerals, we got ancient Paleozoic, Proterozoic metamorphic rocks and sedimentary rocks. There are very few features that you'll learn about in any geologic textbook that aren't found in Death Valley. All of the sedimentary rocks contain beautiful textbook examples of all of the deformation structures and compaction and fossils, and really anything that your heart contents can be found in Death Valley. And the corals. Here's an excellent example, an excellent picture in that Charles Hunt Death Valley book. Sort of about. This is more or less what it looks like in the area, in the basin and range. A good way to visualize it. Is there anything special about Death Valley dolomites to help determine dolomite origin? I don't know. I don't know if any research specifically seeking to determine the origin of dolomite has occurred in Death Valley. I know the limestones have been used to determine relative sea level changes, because they were on a passive margin, so you can determine mean sea level changes pretty easily using some of the limestones. Most recently, what I've read was the Bird Spring Formation, but can't think of anything that is specifically sought out diagenesis or the origin of dolomite as compared to limestone. Those of you who aren't aware of why that's interesting, dolomite contains magnesium. And it's a type of rock that isn't really being deposited on Earth anymore, and hasn't for quite a long time. Some sedimentologists call it the dolomite problem. Why are all these older limestones containing dolomite? A magnesium carbonate, I think it is. Whereas we don't see that anymore, and sort of why that occurs and why it doesn't occur now is really not well understood. So that's a very interesting problem that you can also see in Death Valley, because the old limestones have lots of dolomite. The more recent limestones, even the Tin Mountain limestone, which I specifically pointed out, like this one, is they do not contain as much dolomite. Thank you for joining us, Alexandra. I think I'm just about ready to wrap up here. If you're interested more on Death Valley geology, please check out my YouTube channel, Better Geology, all one word. I've got a number of videos on Death Valley, including the limestones I've pointed out, the ancient lakes that filled the area, limestones as a whole. I've got a number of very interesting topics that I hope you'll all enjoy. Please check those out. That's Better Geology, all one word. It's on YouTube. Hopefully you'll find it. Thank you for joining me here on the Learning Geology Community. Hope to see you all again very soon. Thank you very much. Goodbye.